Every morning, millions of people reach for a familiar plastic handle, expecting it to absorb the exact same pressure as the day before. But applying enough force eventually reveals its failure point. Low retail costs often suggest this is a simple, disposable commodity made from a single type of plastic. In reality, the handle is an engineered, stress-relieved polymer structure designed to flex under specific tension and contour to the ergonomics of the human hand. Producing millions of these identical objects requires a sprawling clinical environment focused entirely on structural consistency. Transforming crude oil derivatives into a resilient tool requires forcing them through a sequence of extreme heat and molecular manipulation. The journey begins in massive storage silos holding thousands of pounds of raw, translucent polypropylene resin pellets. These pellets are fed into a heated chamber, where thermal energy and hydraulic pressure melt them into a fluid matrix. Molten polymer is injected into a polished steel cavity. As it cools, it solidifies into the rigid skeleton of the handle. To prevent the brush from slipping when wet, the handle undergoes overmolding, where a secondary grip material is added to the frame. A soft elastomer layer is injected over the base. As it flows, it locks into microscopic grooves cut into the rigid plastic, establishing a molecular bond. At the boundary where the two materials meet, they fuse into a single unit, inseparable by human force. This multi-material bonding provides the specific ergonomic control and structural resilience required for daily use. With the handle fully molded, the production line moves to the tufting station. Every tuft must contain a specific count of individual nylon filaments to ensure the cleaning surface performs as intended. To ensure alignment, the handles are fed through a multi-axis CNC system, indexing them into position under a bank of needles. In a fraction of a second, a metal picker grabs a bundle of filaments, folds them, and drives them into a pre-drilled hole. These folded filaments are secured inside the cavity by microscopic metal anchors inserted at the same moment. As the anchor forces the bundle downward, it wedges itself into the rigid plastic walls of the handle. The resulting outward tension locks the bristles in place, maintaining the tuft's integrity through thousands of brushing cycles. This sequence occurs simultaneously across dozens of machines on the factory floor, completing thousands of cycles every minute. Tufting balances this high-volume output with microscopic positioning, where thousands of needles move in synchronization. Because the line moves too fast for manual inspection, the factory relies on automated oversight. High-resolution optical scanners evaluate the profile of every brush, confirming that the filament count and insertion angle fall within specified tolerances. Simultaneously, acoustic sensors monitor the vibrations of the machinery to detect mechanical faults that could cause a loss of bristle tension. Even when correctly inserted, newly cut filaments have sharp edges that could damage gum tissue. Under a microscope, a raw nylon fiber presents a jagged surface. To ensure safety, the tip is reformed into a smooth dome. Advanced laser end rounding technology rapidly pulses energy across the tips, melting and shaping the nylon fibers without any physical contact. The combination of automated vision and laser finishing results in a consistent, hygienic surface across every production run. The final stage of production moves into the packaging sector, managed by low-friction robotics. Mechanical fingers place the brushes onto backings, while clear plastic domes are heat-sealed over them. This seal creates a hermetic barrier, protecting the filaments from contamination for months as they move through global logistics chains. Once sealed, the true scale of the operation is visible. Endless grids of identical packages move across multi-tiered conveyor systems. A single production line completes tens of thousands of brushes every hour, repeating the same mechanical sequence without variation. This massive volume allows these facilities to supply the global market while maintaining microscopic precision for each unit. Away from the factory floor, the brush eventually arrives in the quiet environment of a home bathroom. Its appearance hides a journey of extreme heat and high-speed mechanical force, controlled to create a specific hygienic geometry. A user interacts with it for only a few minutes a day. rarely seeing the thousands of robotic operations and sensors that brought it into existence. The next time you reach for this handle and feel its resilience, consider the mechanical complexity required to build it. This everyday tool is the final output of thousands of coordinated mechanical decisions made possible by precise control over temperature and physics.